applied PDE seminar at the University of Washington. Today's speaker is Maria Ntekoume, who is currently at Rice University as an Evans instructor. She did her PhD at UCLA under the direction of Rowan Killip and Monica Visan. She works in the area of dispersive PDEs and integrable systems. And today she's going to tell us about the well-posedness of such a system. So thank you, Maria.
Great. Thank you so much for the introduction and for the invitation, and to all of you for being here. As the title of the talk suggests, it is global well-posedness for the derivative nonlinear Schrödinger equation. I'm going to talk about global well-posedness of the derivative nonlinear Schrödinger equation. And this talk is based on joint work with Benjamin Harrop-Griffiths, Rowan Killip, and Monica Visan. We're all at UCLA. The title of my talk is intentionally a little vague because I want to talk about a few different results in this direction about the well-posedness of the derivative nonlinear Schrödinger equation. So getting started, I need to introduce you to the equation itself. So it looks like this. So we have our solution Q is going to be complex valued. It depends on time, t, which is real, and some spatial variable x, which is in one dimension. But for now, at least I want to keep the flexibility of moving between different geometries, between the line or the torus. So I can pose this equation on both, either the line or the torus. And it looks like this. So we have I times the time derivative of Q plus Q double prime. Prime denotes a derivative with respect to x, our special variable, plus I times the derivative of Q squared Q is equal to 0. And now this equation, if you're familiar with the nonlinear Schrödinger equation, that looks awfully similar to that. It looks very similar to the cubic nonlinear Schrödinger equation. The main difference being that I have this extra derivative here, hence the name derivative nonlinear Schrödinger equation, or in short, DNLS. So I look at this equation, posed with some initial data Q0 that is going to be in some appropriate Sobolev space. And the question that I want to investigate is the well-posedness of this equation. And that encompasses the existence of solution, uniqueness of solution, continuous dependence on the initial data. So getting started slowly, the first things that we want to see is understand at least one of the symmetries of this equation. So DNLS has the following scaling symmetry. If I start with some solution Q to DNLS and rescale it like that, so for some positive constant lambda, I define Q lambda to be the square root of lambda times Q of lambda squared T lambda x. Now this is for any lambda that you give me, this is going to give me a new solution to DNLS as well. And whenever I have a scaling symmetry, that gives rise to a notion of criticality. So we look at these rescaled solutions and we ask ourselves for which homogeneous Sobolev norm does the rescaled solution have the same norm as Q? And in this case, it turns out that this invariant homogeneous Sobolev norm is the L2 norm. This is left invariant under the scaling, and for that reason, we call the problem L2 critical. And criticality is a very useful tool for us because, for one, it lets us make a conjecture. So usually what we expect as a rule of thumb is that if I look at my problem, starting with initial data that have more regularity than the critical one, I should expect the problem to be well-posed. If I start with less regularity, a supercritical problem, then expect the problem now to be well-posed. And then the critical space is this threshold where things get a little bit tricky and interesting. So the critical space, we can think of that as, a target that we can set in the investigation of well-posedness. How low can I get and hope to have well-posedness? For this equation, also the L2 norm has another significance. It represents one of the conserved quantities of the equation. So the L2 norm is preserved under the DNLS flow. And in fact, for this equation, we have many more conserved quantities other than the L2 norm. I have written down the first three of them. One is, as we said, the conservation of the L2 norm. Then we have the Hamiltonian written like this. I wrote down another one, but it turns out there are infinitely many more, and they all look like integrals of polynomials of Q and its derivatives. And as we keep going further down this hierarchy of conserved quantities, the derivative, we get more and more derivatives. And this existence of infinitely many conserved quantities is one indication that our system is completely integrable. Now that we saw these first two things, well, what they told us is that it would be interesting to understand the well-posedness of this equation as low, with regularity as low as possible, if possible, as low as in L2. Now, I want to show you some previous results of what was known when we started looking at this problem, which was a little bit over 2 years ago. And here I want to point out that I am not showing you everything that is known now. I'm only showing you what was known when we started looking at this problem to make things more interesting, because believe it or not, in the past 2 years, there have been so many new results. And there have been huge breakthroughs in the understanding of this equation. Okay, so going in a sort of chronological order, the first thing that I want to talk about is some local well-posedness results that were known. So when it comes to local well-posedness, it was the culmination of works of many people that the problem is actually locally well-posed in HS for S greater or equal to 1/2. And there was no local well-posedness result below H1/2. And as I said, well, if your target is L2, that looks like a big gap, right? Even worse than that, there was a nil-posedness result that came with this local well-posedness result that said that, in fact, below 1/2, uniformly continuous dependence on the initial data is going to break down. So there's no way you can have global well-posedness or even local well-posedness in that sense, if you require uniformly continuous dependence on the initial data, which it sounds devastating, right? If our goal is L2, and even in H1/2, we, uniformly continuous dependence breaks down, that sounds devastating. But it's not as bad as it sounds, right? Because, okay, uniformly continuous dependence might fail, but we can still hope for merely continuous dependence on the initial data. On the other hand, this information still has some bad news in it, right? Because it automatically eliminates some methods that one might hope to employ to prove local well-posedness. The way that these results were proved, and a way that we very often employ to prove well-posedness, is using a contraction mapping argument. But here, knowing that uniformly continuous dependence on the initial data is going to fail, that tells us that below H1/2, we cannot get well-posedness using a contraction mapping argument, because that would give us uniformly continuous dependence on the initial data. And another comment back to the local well-posedness result is, how do we find this time of existence, this local time of existence? So in this result, it is shown that the time of existence depends on the H1/2 norm of the initial data. Even when S is greater than 1/2, it still depends on the H1/2 norm of the initial data. So one would hope that perhaps we can leverage the conservation laws that we have for DNLS. We have infinitely many of them, so we're very happy. Perhaps one of them, or more than one of them, could be exploited to give us global well-posedness. What I mean by that is the following. It is that, well, if I was able to prove something like that, some a priori bounds that told me that my solution at a later time, for my solution at a later time, I can bound its H1/2 norm in terms of the norm of the initial data. If I could use my conservation laws to give me something like that, then I would be able to iterate this local well-posedness and get global well-posedness. Right? But the problem here is the lack of coercivity of the conservation law. So infinitely many of them, except the first one, except the L2 norm, the rest of them are not coercive, which means that in general, they fail to control the HS norms that we would want them to control. Okay, and that actually will become obvious in the results that I'm going to show you now, which are some global well-posedness results. So this is not an exhaustive list by any means of global well-posedness results, but I want to emphasize a few things here. So the first collection of results that I wrote here, you see that we start from H1, then we go to HS, then we go to H1 half, but they all have the same assumption that the square of the L2 norm of our initial data is less than 2 pi. And we see these 2 pi appearing again and again and again. And the reason that this appears is to make our conservation laws coercive and be able to control the corresponding norms that we need to control. And actually, it took quite a long time for this.
Yeah, can I ask a question?
Yes.
So given that the 2 pi shows up because you want to have the conserved quantities be coercive, does it mean that that bound depends on the coefficients that you use to write the equations? So you could write DNLS using different coefficients, right?
Yes.
So would that impact that 2 pi? Because then the conserved quantities would have different coefficients as well.
I believe so. Yeah, it might affect it. It might change it a little bit, but it will still be there. There will be still something.
Right.
I think the 2 pi is that's the L2 norm of the soliton, isn't it?
Yes, of some soliton. I am going to get back to that, actually. Yes.
Okay, thank you.
Yeah, that is a great comment. Yeah, so it actually took a long time to breach this 2 pi threshold. So it was a real problem. It was a problem to breach it, but it was possible. So it eventually happened after many, many years. And initially it was increased by a little bit, 2 pi plus something. And then eventually it went all the way to 4 pi. So we see now in these most recent results, which when we started looking at this problem, that was the state of the art. That we have well-posedness in H1, in H1 half, under the assumption that the square of the L2 norm of the initial data is less than 4 pi. And this 4 pi is also the square of the L2 norm of a soliton. It's the square of the L2 norm of the algebraic soliton. So the algebraic soliton is a solution that looks like this. So let me write it like that, x minus t e to the I ct, something like this. Okay, so the algebraic soliton, the square of its L2 norm is 4 pi. Okay, and it turns out that it required much more work to get coercivity of the conservation laws under this assumption. But in fact, when we started looking at this problem more deeply, what we discovered was that actually this 4 pi is a very, very real problem, because 4 pi is going to be the threshold after which the conservation laws will fail, absolutely fail to control HS norms. And the algebraic soliton is a very good way to see that. So if I take this algebraic soliton and I rescale it in the way that we saw earlier, so take QA lambda for some positive lambda, right, the rescaled soliton, then all of these rescaled solitons are going to have exactly the same conserved quantities, the same M, the same H, the same H2, all of them, or infinitely many of them are going to be exactly the same. However, we can get that the HS norm of these rescaled solitons is going to go to infinity. So there's no way that the conservation laws themselves can control the HS norms. There's no way to get above 4 pi. There's no way to get a priori bounds using the conserved quantities. So it is a very real problem. Okay, and then finally, the last collection of works that I want to show you, again, this is not an exhaustive list, is some results that actually do not have the smallness of the L2 norm assumption, but they require more regularity and spatial decay. So we have results in H22 and in H11 H2. And these works rely very heavily on the complete integrability of the equation they use in the inverse scattering methods. Okay, so what I have said so far has put L2 as the target on which we would like to show well-posedness, or as close as possible to L2. And it has shown us that it is a hard problem, since we don't even have local well-posedness below H1/2. And also there is this 4 pi that keeps appearing again that we saw that actually is a real problem. So one thing to attack this problem, one thing that we focused on was equicontinuity. So we realized, like, okay, we're interested in L2. There is no way that the L2 norm of our solutions is going to grow because we have conservation of the L2 norm. But the enemy is the possibility of the L2 norm concentrating in one or more locations in space. And what can prevent that is equicontinuity. So what we showed was the first result that we showed was an equicontinuity result. This is joint work with Rowan Killip and Monica Visan. So I should say at this point that I don't remember if I said at the beginning that the results that I'm going to mention are joint work of different subsets of the 4 of us. So we'll try to make that explicit whenever I mention a result. So the first collection of results are from our first attempt at this problem with Rowan and Monica. So the first result we showed was an continuity result. So if we start with a set of initial data bounded in L2, equicontinuous, that satisfies this smallness assumption for the L2 norm. So we want all initial data in Q. We want the square of the L2 norm to be less than 4 pi. Again, the same 4 pi that we kept saying earlier. Then if we look at the set Q star, which is all the states that can be reached by DNLS orbits that originate from Q. So I take some initial data in Q, and then I flow it under DNLS for time t, and I take the collection of all of these things for all different initial data and all different times. That's Q star. Then this set is also going to be L2 equicontinuous. So if I start with an equicontinuous set, Q star is also going to be equicontinuous. If I also have this assumption, that's the first ingredient. Now, once we established this L2 equicontinuity, we were able to show some a priori HS bounds. So for S between 0 and 1/2, and some set of initial data Q that is bounded in HS and again satisfies, oops, oh, I'm so sorry. I don't know what happened here. Oops, this is, doesn't move. Give me 1 second. Yeah, I don't know what happened to my slides. Oh, okay, it seems to be working now, I'm sorry. Okay. Yes, so we start with some set of initial data Q that is bounded in HS and still satisfies the smallness in L2 norm condition. Then we can show a priori bounds in HS for all Q in Q star in terms of the L2 norm of the initial data and the HS norm of the initial data. And if the set we started with Q was also equicontinuous in HS, then Q star is also going to be equicontinuous. And now, once we have these a priori HS bounds, we can use them to prove global well-posedness. So for S between 1/6 and 1/2, the DNLS evolution is globally well-posed on the line and on the torus for all initial data in HS that also satisfy this smallness in L2 norm assumption. Okay, so these first 3 results that I showed They hold both on the line and on the torus in both geometries. So we are able to get under the smallness in L2 norm requirement, we are able to get global well-posedness all the way down to H1/6, which at the time that was a big step, given that not even local well-posedness was known there. And it also, even this 4π assumption, it matched what was already known, H1/2 and above. Okay. Now, the next result that I'm going to show, they only apply on the line, so we don't have their counterparts on the torus as well. So after the first results that I showed you were completed, this is work of Ben, Rowan, and Monica that were actually able to remove the smallness in L2 norm assumption from the continuity result. So they show that if you start with an L2 bounded set of initial data, if it is equicontinuous, then Q star is also going to be equicontinuous. So no more smallness in L2 required. And once the smallness in L2 norm assumption is removed from the equicontinuity result, it turns out that that is all you needed. So in the previous results that I showed you, we kept having this assumption that we kept having this 4π bound here and here, but the only reason that that was there was to ensure L2 equicontinuity. If you have L2 equicontinuity, you don't really need that. Okay, so once Ben, Rowan, and Monica removed the 4π L2 norm assumption for equicontinuity, that automatically gave an improved result for global well-posedness. So we have global well-posedness in HS on the line for S between 1/6 and 1/2. Okay. And then the last result, which actually manages to go all the way down to L2 on the line. That is joint work with Ben, Rowan, and Monica, all four of us this time. And we showed that DNLS is globally well-posed in L2 on the line. So the critical space, exactly what we wanted. Okay. Great. So now I will try to say a few words about the methods that go into these proofs. Of course, there are many results that I'm going to discuss, so not everything is going to be explained in a lot of detail, but I want to give you at least an idea of what goes into the proofs. Our approach of the problem really relies on the completely integrable structure of the equation. So complete integrability has many ways to show itself. One of them is the existence of infinitely many conservation laws, which we discussed earlier. I wrote them down here again. And we also have already seen their shortcomings when it comes to helping us approach global well-posedness. Another way that complete integrability shows itself is the existence of a Lax pair. So a Lax pair is a pair of operators, L and P, with the following property. So Q is a solution to our equation if and only if the time derivative of L is equal to the commutator of P and L. And because of this, we see that the spectral properties of L are going to be preserved under the flow. And then the question is, how do you use that to your advantage? How do you use that to show you something? So I have written down here the Lax operator for DNLS. So we have L of kappa given like this, and our kappa is going to be greater or equal to 1. And in particular, when we set our potential Q to be 0, we get L0 given like that. So what we use to capture this preservation of the spectral properties of L and give us something that is useful to us is the perturbation determinant, which is something that people have been using for a long time. So we look at the determinant of L0 inverse L. That is the perturbation determinant. It turns out that this is not exactly the object that we want. That actually goes back to previous work of Rowan and Monica. It's where it's, their joint work with Chang, where they proved conservation. They found new conservation laws for KDV, NLS, a variety of equations. So it turns out that it is better sometimes to, instead of put the inverse of L0 either on the left or on the right, to put half of it on the left and half of it on the right. It allows you to, well, in some scenarios, it allows you this object that you define to make sense for the Q in the regularity that you want, or it gives you access to exactly something that is more useful to you, which is the case here. And then this eventually leads us to consider the determinant of 1 minus I kappa lambda gamma, where lambda and gamma are written down here. And I think it's fairly easy to see how from this we go to this once you look at the definition of lambda and gamma. So lambda is kappa minus partial derivative minus 1/2, q kappa plus partial derivative minus 1/2, and then gamma is defined like that. This quantity here is a quantity that is very important to us. We call it A of kappa, and we need one more renormalization to make that even better for us. So we consider alpha of kappa, which is minus the logarithm of A. And that actually has the advantage that it can be written as a series like that. So we can write it as the sum of 1 over L times the trace of I kappa lambda gamma to the L. It turns out that this alpha of kappa is preserved under DNLS for all kappa sufficiently large. So these are our new conserved quantities that are going to aid us in our study. These new conserved quantities were already considered in the work of Klaus and Schipau, which was announced in the summer of 2020, if I'm not mistaken, which was while we were also working at this problem. So what they did in their work was they defined these quantities and they actually used them to get a priori HS bounds. So something very similar to the result that I'm going to show you. But the difference is that in this smallness of the L2 norm assumption. So for us, smallness in the L2 norm means less than the square of the L2 norm has to be less than 4 pi. In their work, the L2 norm had to just be very, very small. Okay. And that was not quantified. It had to be sufficiently small for something to work. And you will see what I mean very, very soon. So now I want to show you how these new conserved quantities, alpha, really give us access to the continuity. So for a set Q to be equicontinuous in L2, perhaps a more convenient way to think about it is as tightness on the Fourier side. So we need the L2 norm of the high frequency part of Q to converge to 0 as n goes to infinity uniformly for all Q in Q. And let's see how alpha can capture that. So we saw that alpha has the series expansion. We know that alpha is conserved under DNLS. And if we look at the first term in our series, or when L is equal to 1, we're going to get the quadratic term of alpha, right? Because each copy of lambda and gamma comes with one copy of Q in there. And we can actually compute exactly what that is. So we compute that the imaginary part of the first term is the integral of 2 kappa squared Q hat squared over 4 kappa squared plus C squared dxc. So that is not exactly what we want yet. So we need to work on it just a little bit more. Jumping off of alpha, we defined beta, which is the square of the L2 norm minus 2 times the imaginary part of alpha. Now, since the L2 norm is conserved and alpha is conserved, beta is also going to be conserved under DNLS. And if we look at the quadratic term of beta, which I'm going to denote by beta 2, that is, well, the square of the L2 norm minus 2 times the quadratic term of alpha. And what we get is the integral of xi squared over xi squared q squared over 4 kappa squared plus xi squared. And that actually is exactly what we want, because this captures the square of the L2 norm of the high frequency part of Q, right? Which we can see from this inequalities, right? So this is very useful because it tells us that our set Q, I'm not sure where I can write here, it tells us that our set Q is equicontinuous in L2 if and only if beta 2 of kappa Q converges to 0 as kappa goes to infinity uniformly. Okay. Okay. So what we want to show is get equicontinuity is this essentially. Okay. Now the first attempt is the following. Our conserved quantity beta is the quadratic term plus the rest of the series. And since beta is conserved, I can write beta 2 as a time t as beta 2 a time 0 plus the difference of the tails. Right? Now, I start with a set of initial data that is equicontinuous, right? So this goes to 0 uniformly. If I was able to show that this, to get control over this, if I was able to get control over this, either to show that it is bounded by, that the tail is bounded by beta 2, or if I could show that this goes to 0 uniformly as kappa goes to infinity, then I would be happy. I would have finished, right? However, the estimates that we have, the naive estimates that we can use to try to bound the tails are not enough. They're not sufficient to control that sum. And that is precisely where in the previous work of Klaus and Shiba that I said, there was some really smallness of Q that was required to get control over the tails. And that is also in our work where this 4 pi assumption comes in. This 4 pi assumption is essentially the only way that we can find to make sure that the tails are controlled. That's exactly where this 4 pi assumption comes in controlling the tails. And I'm going to leave it at that. Now, moving on, once we have L2 continuity, how do we get the HS bounds? We turn again to our nice conserved quantities, beta. So now we're going to take beta, and to access our HS bounds, we're going to take beta and integrate against some power of kappa, and this new quantity is going to be called beta s. Of course, since beta is conserved, beta s is also going to be conserved. And doing exactly what we did before, we look at the quadratic term of this conserved quantity. So the quadratic term here is going to be something like this, which once again, it looks great to us because it controls the square of the HS norm of the high frequency part of Q. And working again like before, this is the thing that we are interested in. This is what is going to give us control over our HS norms. And this is conserved, so all we need to do is control the tails. But in this time around, we can, once we have the L2 continuity, we can control the tails, right? We don't need the L2 norm assumption anymore as long as we have the continuity. So that is essentially what I want to emphasize here, that in order to close this estimate, we do not need to rely on any smallness on the L2 norm anymore, as long as we have a continuity. Okay. Okay, great. And then we are able to control the quadratic term beta s in later times in terms of the quadratic term of beta s at time for our initial data, plus some constant times the square, the fourth power of our L2 norm of the initial data. Okay. And now finally, having these a priori HS bounds, how do we use them to get global well-posedness? As I said earlier, we don't, going into this question, we didn't even have local well-posedness. If we had local well-posedness and we were able to control the time of existence by the HS norms, that would be great. But in this case, we didn't have that. We didn't even have local well-posedness. So for that, we use the method of commuting flows that was introduced by Rowan and Monica for the KDV equation. So our conserved quantity alpha admits the following asymptotic expansion. So alpha is I over 2 times m, which was the square of the L2 norm, plus 1 over 4 kappa h, which was our Hamiltonian, plus some lower order terms. And if we kept expanding here, we would recover all the previously known polynomial conservation laws that we saw at the beginning, or we saw 3 of them, but you believe me that there are infinitely many of them. So now, inspired by this, we define h kappa to be 4 kappa times the real part of alpha. And the reason is the following. So here, if we go and take the real part of alpha, that is going to be equal to this, right? This term goes away because m is real. It's the square of the L2 norm. If we also multiply by 4 kappa, then we're going to get h of q plus, again, O of kappa to the minus 1, right? That's exactly what we have written here. So h kappa, defined like that, is h plus some small error. Okay, so h kappa converges to h as kappa goes to infinity. And moreover, these Hamiltonians h and h kappa define commuting flows. The continuity in the HS bounds that we discussed earlier, they hold not only for the DNLS equation, but they also hold for these h kappa flows. So we can have HS bounds also for the h kappa flows that are induced by these new Hamiltonians. And it turns out that it is better to start looking at the global well-posedness of these h kappa flows. It is actually quite easy to prove that they are globally well-posed in HS for all s greater or equal to 2. So all the way down to L2, we can get global well-posedness for these h kappa flows, and they commute with h. And our hope now is that these h kappa flows are actually going to converge to DNLS as kappa goes to infinity. Okay, so the idea is the following. So we want to show that if we look at the difference flow, the Hamiltonian h of DNLS minus this h kappa Hamiltonian, if we look at the flow induced by this difference, we want to show that that converges to the identity as kappa goes to infinity. Okay, so we want to show something like this, starting with some initial data q in q, the difference of I take q and I flow it under h minus h kappa for time t minus q. That is going to converge to 0 in hs in any bounded time interval uniformly, okay, for all q in q. Once we show that, then we will be able to essentially get the global well-posedness, as I will show later. What I want to emphasize is that this is precisely where the s greater or equal than 1/6 assumption is required, and it doesn't allow us to go lower than h1/6. This is precisely the point, because as I said, the h kappa flows are globally well-posed all the way down to L2, so there is no issue there. The issue comes from trying to estimate this, from trying to show that the difference flow converges to the identity. Okay. Okay, great. Now, once we get that, how does that give us global well-posedness? Well, global well-posedness to us, the way that, the notion in which we say that DNLS is globally well-posed is in the sense that the data to solution map can be extended from, say, Schwarz solutions, okay, continuously. Okay, so starting with some initial data, if we start with some initial data, Q0, let's say, we can approximate it with by some sequence of nicer data, let's say Schwarz. Okay. Now for this nicer initial data, we have global well-posedness. So all we need to show is that at later times, the DNLS evolution of these initial data is going to converge to something, and that is going to be exactly our solution with initial data, Q0. Okay, so all we need to show is that if we have a sequence of initial data, Q and 0, that converges in HS and satisfies our L2 smallness assumption, then for any positive time t, the DNLS evolution of this initial data is going to converge in HS uniformly for t between negative t and t. So all we need to show really is that the sequence at time t is Cauchy. So if we look at the difference Qn of t minus Qm of t, we can break it into the following sum. So we can break that into this difference plus this difference plus this difference, right? So this is the DNLS evolution of Qn0 minus the H kappa evolution of Qn0. Now, since H minus H kappa converges to the identity, this is going to converge to 0 precisely by this. Okay. And the same thing happens for this difference here. So this is the H kappa evolution of Qm0, and this is the DNLS evolution of Qm0. Again, precisely from this is going to converge to 0 in HS. And now when it comes to this term, that is the H kappa evolution of Qn0 minus the H kappa evolution of Qm0, that is certainly going to converge to 0 because H kappa is globally well-posed. Okay. So once we have, so from what we discussed earlier, this is going to converge to 0 in HS as n and m go to infinity. So that sequence is Cauchy, and the limit that we're going to get for Qn of t is going to be our solution. Okay. Okay. Now, after we, well, essentially not after, but while we were completing this work, there were actually some very, very exciting news. So about a month before we announced the results that I just discussed, there was this very exciting new work by Bahri and Perlman, who showed global well-posedness in H1/2 on the line without any assumptions on the L2 norm. And I'm sure now hearing about that, given all we have been through and everything we have seen about this 4-pi appearing again and again and again in all these different works, that sounds like a big deal, and it is definitely a big deal. It was it's a very exciting result. Okay, so that was actually, very encouraging towards possibly removing this 4-pi L2 norm assumption for equicontinuity as well, and for the results that I discussed earlier. And it didn't take long until that actually happened. So Benjamin, Rowan, and Monica were able to remove the L2 norm assumption for L2 equicontinuity on the line. And as we discussed earlier, this automatically extends the global well-posedness in HS for S between 1/6 and 1/2 to initial data with arbitrarily large L2 norm. Okay. 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 So now having the L2 equicontinuity without any assumptions on the L2 norm, the next goal was to try to investigate well-posedness all the way down to the critical space L2 and see what gives us. Okay. So let's think about all the ingredients that went into our proof earlier. We have the continuity, the HS bounds, we have these things, that's great, but the important thing that we need to focus our attention to is the commuting flows, right? So we saw earlier that the H kappa flows were globally well-posed in L2. That was already, we had already done that, so that was not an issue. The issue was showing the convergence of the difference flow to the identity in L2. Okay. And you might think that the problem is this. The problem is that I want the L2 norm of the difference to go to 0, but that is actually not the problem because of the continuity. Because of the continuity, if I want to show, let's say that Qn, I'm not sure how I want to write that down. If I have that Q, let's say that I have, let's say, a family Qn that is equicontinuous in L2. Okay, if I can show that Qn converges to 0 in H, I don't know, minus 100. Okay, it doesn't matter in any lower Sobolev space, that will automatically give me convergence in L2. Okay, so that is actually not the problem. The problem is that what we saw earlier was that in order to show this convergence, we required Q to be in H16, right? So we would require additional regularity on Q to be able to replicate that argument, and that regularity cannot come out of nowhere since now we're working with initial data that is in L2. So the solution to that is to use local smoothing. So locally in space-time, we can have a derivative, okay? That is what the idea of local smoothing is, more or less. So what we were able to do is prove the following local smoothing results. So we showed that if we start with a set of initial data Q, that is in L2, bounded and equicontinuous, and some C, as far as function C, you can think of that as a smooth cutoff. That's not very important. Then for each positive t, the solutions to DNLS with initial data in Q are going to satisfy the following. So if I integrate the following, so if I take the H1/2 norm of this localized Q, okay, square it, and then integrate on this bounded interval of time, that is going to be bounded in terms of the square of the L2 norm of my initial data. So I'm locally in space and time, I'm going to gain half a derivative, okay? So even though my initial data was only in L2, locally in space-time, I can do a little bit better. Okay? And we proved this result not only for DNLS, but also for the difference flow. And actually what we really need is for the difference flow, right? Because this is exactly what we want to estimate later on. Okay, and the idea to prove behind proving local smoothing relies once again on alpha, on our conserved quantities alpha. So, but it relies on a microscopic version of this conservation law. So we can write alpha as the integral of our density rho, and we have microscopic conservation laws for that. We have one for DNLS and one for the difference flow. So if we multiply by our cutoff and do integration by parts, we get an equality like that. And then what we need to do is, well, it turns out that this quantity here is going to capture this extra local smoothing that we were seeing. Okay, so this is going to capture something like this. Okay, and then we will be able to bound it by the L2 norm of the initial data. Okay, so using this local smoothing, we are able to prove a local version of this convergence of the difference flows result. So it's no longer the difference evolution of Q minus Q that converges to 0. It's a local version of that, right? So I need to multiply my solutions by C. Okay. And working exactly the same way as before, decomposing the difference of Qn of t minus Qm of t like before. Well, now that has to also be multiplied by our test function. So we are able to replicate the same argument and get that this difference now converges to 0. So we get convergence not of Qn of t, but of C Qn of t. And now the next question is what happens? So I understand now what happens to my solution locally, right? On a bounded interval. But what happens to my solution as I move towards infinity in space? Well, for that, the solution to this question is tightness. So we also prove a tightness result. Let me quickly remind what tightness means, or what our version of tightness is going to be here. So we can consider an even smooth non-negative function phi such that phi is greater than 1 for x greater than 1, and then we rescale it like that. So this new function is greater than 1 outside the interval minus r. And we say that a bounded subset of L2 is tight in L2 if the integral of q squared multiplied by phi r goes to 0 as r goes to infinity uniformly for all q in q. Okay, so our tightness theorem says that for any positive time t and an L2 bounded set Q of initial data that is equicontinuous and tight, Q star is also going to be tight. Okay, so tightness is preserved by the DNLS flow, and that allows us to also control what happens outside, what happens close to spatial infinity. Okay, and that essentially closes the argument. Okay, so thank you very much for your attention.